All right, so let's try an evasion attack. This is one that lets you see. Now, we tried an evasion attack. Well, we tried a poisoning attack. It's the only attack we've done so far where we relabeled some of the numbered images with the wrong label to fool the machine learning model. Now we're going to do an evasion attack, which is modifying an image so it will be misunderstood by the model. So in order to do that, we're going to use the SecML library, which is a machine learning Python library intended for security tasks like this, as opposed to sklearn, which is just a learning model. This includes a bunch of functions just to help you perform machine learning attacks. So we're going to need a data set. So here's another one of these simple data sets, just so we have something to work with. And okay, it's downloading and installing some code up there. Let me run this, get this one ready to go. And let's wait for the previous one to end first. It's successfully installed. There, it's done. All right. So now I'll run this one. This is going to make a set of points and plot them out so we can see them. You can tell which command is running by looking for a little green arrow here. There it is. So it is importing a random blob function, and then it's going to create a random blob with clusters. You can see in these coordinates, -2, 0, 2, -2, and 2, 2. So it's going to make 3, I think, Gaussian clusters. And we'll see them here. So you end up with 3 categories, and they overlap somewhat. All right, so now we have some data. All right, and now we're going to make a support vector machine. Like I said, if you have 2 categories, either of these lines would do, but in fact, you want to choose the line that gives you the widest road, the margin here between them. That's how you do it. And in this case, we're going to use a generalization of the model where it allows some errors. It doesn't require perfect separation. Obviously, you're not going to have that, but it will take a sort of weight function and consider some of the points near the line to find the best line that does the best job of separating these. So here's the scalar vector machine, support vector machine model. So it makes a 3-fold splitter to split it into 3 groups, and then find the parameters, and 98% accuracy. And we can visualize the results, which is, of course, the nicest way to understand them, by plotting out the data and the lines between the categories. There you are. So you see, these are the separation borders it discovered. And they're not actually required to be straight lines anymore. They can have some curve to them. But this is the 98.8% successful. And you can see it's got a few green dots it got wrong here, and that looks like the only errors. So, all right. Now we're going to do an evasion attack. And here's an example of a real evasion attack. You have a model which can tell one animal from another. You train it on animal pictures. And so if you give it a panda, it takes this image, which is just a little bit blurry, and it calls it a panda with 57% confidence. But if you add less than 1% of noise to it, so here, to a human eye, it looks just the same. But a little bit of noise causes it to decide that it must be a gibbon with 99% confidence. And this is a real important fact. Machine learning models do not work the way our eyes do. So to a human, your eye picks out the shape of this ear and the shape of these eyes and the snout. And now, even though there's some noise, you still see those features, so you recognize it as still the same thing. But the machine learning model has done some kind of mathematical combination of several of these pixels to decide, and you don't know which pixels or what the weights were. It has chosen some strange other way of deciding whether this is a panda or not, and this noise is disastrous for that. And there was a study, I probably mentioned it already in this class recently. China apparently has a bunch of robot taxis already out there. And they took some researchers, I think in California, took the system that they're using in those robot taxis, and they carefully planned a little bumper sticker looking thing with shiny and colored dots on it. And they said that if you stick that on a car, that makes the car invisible to the robot taxi, so they will ram right into it. They said you could easily make an attack where you fly a drone out there and hold this little placard in front of somebody's car, and now the taxi will just ram into it. Because, even though the car is still there and a human could still see it, some subtle changes in the appearance of it are enough to completely cause the machine learning model to misinterpret the data and not think that there's a car there. So that's an important thing to know. And that's called an evasion attack. So what we're going to do in this evasion attack is we're going to move a point to a location that causes the model to misidentify it. So this is going to take one point and figure out how far it has to move that point to make the model misunderstand it. And that's why it's using this SecML library to perform the attack, which uses information about how the model works, its weights and such, to mathematically calculate what the most effective move is. And so it takes this red dot and moves it up here, and now the model misidentifies it. All right. Now we can run a test to see how much the model degrades under various attacks, to see how much our model can survive various types of evasion. And that's going to take several minutes to run, so I think I'll just jump to the answer. You see, as if you tell it how far it's allowed to move it, then you see the accuracy. So if you move it by 0.1 units, then you lose maybe 10% of accuracy. And if you move it by like 0.6 or 0.7 units, the accuracy falls down to essentially random chance, because remember, there's 3 categories. So you'll get 33% right just by random chance. So this is a way to measure how strong your model is. How much can your model withstand poisoned images? And that's a measure of its quality. So there's some flags to get there in various ways. And here's a noisier problem where you can see what distance has to be moved. So this is a little bit abstract, but it's a way to see how much models can withstand modified data. So let's stop this recording.